assume the variance of the error term must be the the same. But now we will discuss what is the implication when we have the variance of the error term not to be the same. So we have unequal value of the error term, the ui, the error term. So recall that one assumption, so it is assumed one assumption on the squared assume homoscedastic or constant variance of ui. But now when the variance of ui is not the same, not equal, not constant, so what happens? Okay. So assumption of the classical linear regression model state that the disturbance should have a constant or equal variance independent of I. So meaning that the yi. So this one doesn't matter what the value of which observation. So yi. So y1 or y2 or any y. Okay. So doesn't matter of the position, doesn't matter which observation. So independent of I, it has all have the same constant value of variance or error variance. Therefore, having an equal variance means that the distributions are homoscedastic. So we need the error term. We need the error term to have homoscedastic error variance. So the same or equal value of variance for the error term. So if the homoscedasticity assumption is violated, then so meaning that different observation has different value of variance. So we have sigma I square. So previously we don't have I. Okay, the variance of ui is just the variance, it's just the sigma square, the variance. So it doesn't matter what the value of I, it doesn't matter which observation, all has the same variance, sigma square. But if let's say the variance depends on the observation, so different observation has different variance, so sigma I square, so it depends on the observation. So meaning that so we have heteroscedastic error variance, meaning the variance are not the same, and it is depend on the observation, the I. So where the only difference is the subscript I attached to the sigma I square, which means that the variance can be changed for every different observation in the sample. So for I equal to 1, 2, 3 up to plus 1. So look at the following graph, for example. So this is an example of homoscedastic. So we want our model to have this kind of spread of error. So we need our error to have the equal spread, so that they have a constant variance. So this the assumption that we have on the real square assume for the error to behave like this. So this is what we call homoscedastic error variance or homoscedasticity. So we need our error to have the spread like this now. This is heteroscedasticity, the example of heteroscedastic error variance, as well as this one. So these two. So mean that the spread of the error not the same, so unequal. So this one equal, so doesn't matter of I. I mean the error is just around, just the same distribution, the same spread of the error. Okay. But this one, this is unequal. This one unequal. This one also unequal. So this is an example of the case of heteroscedastic error variance. This one also the same. So first graph represent homoscedastic error variance. So again, this is what we want to have, our model to have. Second graph, example of, for example, income consumption pattern for low level of income, not much choices opposite for high level. So for example, this one. So let's say you have income. So this one is consumption. Let's say your Y is consumption, your X income. So for those with higher income, the way that they consume, there is a large variation. What we call that? There is large variation. Okay, so large variation among the people that has higher income. Some of them consume just a small portion of their income. Some of them consume large portion of their income. So that makes the variation to be higher. as compared among those who has lower income. So lower income, they don't have much choice, so they have, all of them must consume last portion of the income. But for those who has high income, it depends. Some decide or choose to only spend small portion of their income to consume, and then the rest goes for what we call saving, for example. But for some of them, they spend or they consume last portion of the income, so makes the spread of their what we call the error to be larger as compared to for those who has low income. So this kind of situation can make or can be the reason or to be the source of the heteroscedastic error variance. So again, this is an example of one example. So this is also possible, although I think for many cases we have this kind of error variance when we have heteroscedasticity problem. But it is also possible to have something like this. Meaning that for larger value of x, the spread is going to be narrow, smaller as compared to those as compared to when x has a smaller value. Okay. So as an example given here, so improvement in data collection. This is an example, just one example that can produce this kind of heteroscedastic error variance. So the third one, the graph improvement, for example, improvement in data collection techniques or two error learning model experience decrease the chance of making large errors. So let's say y represent number of errors made, and then your x represent the number of years working experience, for example. So I mean, for those who has longer working experience, the what we call that the variation of the error among those groups of workers is going to be smaller as compared to those who has lower working experience. Okay, so have higher wider spread of the distribution. So it makes the error to be higher as compared to this one. So it's possible, okay, it's possible to have this kind of error. So the implication or consequence of heteroscedasticity, just remember that the present is just like multi-connectivity. So just like the multi-connectivity problem, the present of the problem does not make the estimator to be biased. So it's still unbiased. Okay, meaning that the average of all possible estimates is going to be the same to the true value of parameter, but it makes the present of problem we give the implication on the estimate of the error, the variance of estimator. So it is still unbiased and consistent. This is because none of the exponential variables is correlated with the error term. So a correctly specified equation will give us values of estimated coefficient which are very close to the real parameter. However, the present of heteroscedasticity problem will affect the distribution of the estimated coefficient. It can increase the variance of distribution and therefore making the very square estimator to be inefficient. Okay, so recall that what the meaning of efficient estimator that we discussed earlier. Efficient estimator means that it is unbiased and it has the smallest variance among the linear what we call that among the unbiased estimator. And it's also possible that the present of heteroscedasticity will underestimate the variance of estimator, leading to higher value of t and error statistic. Meaning that the present of heteroscedasticity will make the estimate of the standard error as well as t statistic to be less reliable, just like multi-connectivity, the one that we discussed earlier last week. Okay. So meaning that the chance for us to make incorrect conclusion higher when we have the problem. So meaning the chance of us, for example, to reject or not reject, although the true value is correctly specified by the null hypothesis, but we reject. So the chance for us to make incorrect conclusion, not decision, we decide correctly based on the p value, based on the critical value, compare the test statistic critical value, we decide correctly, but the correct decision doesn't mean that we make the true what we call conclusion, the correct conclusion. Decision conclusion is different conclusion about the hypothesized value, whether it is true equal to 0 or not equal to 0, for example. So to detect heteroscedasticity problems after your estimates, we have to check lah. So after you estimate, you have to check whether there is multi-equality problem. So last week we discussed for the case of multi-equality, if the problem is not that serious, you can just ignore it. But if there is serious problem, that makes your estimate to be not significant or insignificant, although we believe that it's supposed to be significant. So you check VIF, for example, and check and you see high value of VIF, and then you have to do something. You have to make correction or remedy the problem. Okay. So for the case of heteroscedasticity, you need to do the same. You have to check. We have a number of tests available for us to check for the presence of heteroscedasticity problem. And then if there is a problem, then you have to fix the problem. You have to remedy. You have to fix the problem. So the first is the informal. So there are two ways in general. The first is the informal way, which is done through the graph by inspecting the graph, and therefore we can call it the graphical method. So normally we can check, we inspect the error, the residual. So remember that we estimate this one, the error term or disturbance. So we estimate we use residual as estimate. So residual just the difference between y minus y hat, residual. Remember, the actual value minus the predicted or fitted value, that is our residual. So we use residual as estimate for the error term or disturbance. So after you estimate, and then you have to check your residual in order to see if there is the presence of heteroscedasticity problem. So through graphical inspection as well as for choosing numerical approach to perform the test. There is a number of different tests available. The second is through formal test for heteroscedasticity, like the following one. So we have the Goldbach-1 test, the Birch-Pagan-Godfrey LM test, the Getzer LM test, the Harvey LM test, the Ingle-Ash test, War test. So basically, each of these tests allow us to test for different types of heteroscedasticity or heteroscedastic error variance, because there are different possible patterns of heteroscedastic error variance. So each of these allow us, especially this one. So the LM test one, the Birch-Pagan, Getzer, Harvey, and Ingle. Basically, each of these allow us to identify for the specific pattern of heteroscedastic error variance. The white test combination, the white test. Okay, we look at the next one. I will explain again where we discuss about the test. So for the case of graphical inspection, what you can do after you estimate, you get your residual. Okay, you have residual after you estimate, you have residual, and then you inspect the residual. What you can do, for example, you can produce plot of the square of residual against the fitted value or against each of x. Okay, so if you are able to see something like this, so this is a homoscedastic error variance. So just the same spread. Okay, so this one okay lah. If you have something like this, then okay. So plot the square of the obtained residual against fitted value of y or x, and we see that we inspect the pattern. So evaluate the pattern. If you have something like this, if the square of residual, you produce plot against the fitted value of y or each of x. Let's say you have 2x, you have to do 2. You have to produce plot against x1 and then x2 and see. That allows us to identify which x is the cause of problem. So which x that produce the problem. Okay. So you have something like this. This means that the unequal spread of error variance. This one also the same. So this one also unequal. This one is another type. This is also possible to have something like this. So I mean there are a number of different pattern or possible types of unequal spread out error variance or heteroscedastic error variance. So the compact quantized is just the easiest approach. Let's say you only have Excel, for example, then you can easily perform this test in Excel. So this is quite easy. I mean, but EDUs does not provide us this test. So EDUs only provide us the rest of the test listed earlier. But this one is not given. But this one can be considered as a simple way of testing if the model we estimate, regression model or ecological model that we estimate has the problem of heteroscedastic error variance or what we call heteroscedastic problem. So the step as given here, the first step, identify one variable that is closely related to the variance of estimate. So after you estimate and then when you expect true graph like before, you have to identify which X that produce unequal spread of error variance, something like this. So and then you order or sort the observation of this variable in descending order, starting with highest and going to the lowest. So this one, either one, whether you sort from the smallest to highest or highest to smallest, doesn't matter. Okay, but what important when you calculate the F test statistic, the higher must be above, smaller must be below. So split the ordered sample into two equally sized subsamples by omitting the cis-sectoral observation, so that the two samples will contain half of the remaining observation. So let's say we have example. Let's say originally we have 18 observation. So we remove 1/3 of them. So we remove the middle 6 observations. So we only have remaining 12. So 12 divided by 2. So we have 6 for the first subsample, the second subsample, 6 observations. Yeah. So there is no clear guideline on how many observations should be taken out. So you have to decide. So if you have small sample, you have small size of sample, do not take out too many observations. If you have larger sample size, then you can remove a larger observation in the middle. So again, you sort the data based on the X that you believe is the solved problem. So how to know which one? One way is by inspecting the graph. So you produce, as you estimate, you get the residual, you plot a square of residual against each of X and see which one has the heteroscedastic error. Alright. And then you sort, you remove the middle part, and then you estimate two different models, run on the square regression of Y on the X variable that you have used in step 1 for each subsample and obtain the SSE for each equation, and then you can calculate the F statistic. So where SSE1 is the SSE with the largest value, and then SSE2 is the smaller one. So again, doesn't matter whether you sort from smallest to highest. What important is one, larger value should be above, and then the smaller value of SSE should be below. And then you compare the F test statistic with the critical value from F table. So degree of freedom is given here. So there are two degree of freedom. So the N sample size for the first subsample minus K minus 1 minus number of independent variable, and then minus 1 minus 1 another 1. Same for the second one. So and then reject if the F statistic greater than the value. So reject now. The noun of homoscedasticity. So the noun is the error variance are the same, alternative not the same. So we split data into two. You have a set of data, you sort data, and then you remove the middle part, and then you estimate two different models. The first part, and then the first one, and then the last part. So the middle they exclude, the middle part you exclude, and then you calculate the F statistic and then compare to the critical value from F table. Then you decide, make a conclusion. So for this example, we have the data. So this one, okay. So data, let's just see this one. for this example, we simply use by model. So two model that has only two variables, y and x. So our y is the R&D expenditure for different companies, and then we have independent variable, the sales, the amount of sales. So this one, so we have expenditure for 18 different companies, sales and R&D expenditures. So the square R&D expenditure as a function of sales. So we need our independent variable R&D expenditure and our sales as the expenditure variable. So this one, if you okay, so for this kind of data, you can see that we have different size of companies. Some companies had larger sales and larger value of, like both X and Y as compared to some has smaller value. So this can produce can be the reason or can produce the problem of heteroscedasticity. Meaning that the error is going to be something like that. Whenever you have this kind of variables, let's say you have you have a data set. In the data set, some of them has large value. For both y and x, some have small value. So if you produce when you estimate, it's quite likely that it will produce this kind of error lah. So meaning that large company to have large variation and small companies to have small variation. So it will make the error to have different size. Okay, and then to produce different size of error variance. So for this kind of data, we are able to, we can suspect that there's possibility to have the problems of heteroscedasticity. So we need to test. We need to test to make sure, to ensure, or to check, or to identify whether it has the problems or not. So for this one, we suspect that there may be heteroscedasticity problem in the regression. R&D expenditure variation is larger for the companies with bigger sales value than the smaller companies. So to perform the test, you need to remove the middle part. You need to sort first, but the given data is already sorted from smallest to highest. If you check, so if you inspect the data, so basically it's already given from smallest to highest, smallest to highest, so it's already sorted. Okay. So what I need to do next is to remove the middle part. Okay. So let's say we remove the one third of the observation. So we have 80 in total. So we remove 1/3. So 6 lah. So 6 in the middle. So from number 7 to we remove number 7 to number 12. Okay. We don't need to remove it here. What you need to do when you estimate the two model, you just choose the number of variables that you want to estimate. So for example, this one, after we sort, the data is already given in order. So smallest to highest. So I mentioned before, doesn't matter from smallest to highest or highest to smallest, doesn't matter. Okay, what important, later when we calculate this one, the larger value must be above. Larger value divided by smaller value. Okay. So this one, okay, let's say here we decide to remove 6 observation in the middle. So we estimate the